Pluto is 3.67 billion miles from Earth. At that distance, even a radio signal traveling at the speed of light takes more than 5 hours to make a single trip. No human has ever been there. Only one spacecraft has ever flown past it, and that was a brief encounter before the probe continued deeper into the solar system. For decades, Pluto remained one of the most mysterious objects in our solar system. It was simply too small, too distant, and too faint for scientists to study in the kind of detail they wanted. Then James Webb Space Telescope arrived, and astronomers gained a completely new way to investigate this frozen world. To understand why Webb's observations matter, we have to go back to Pluto's discovery. Pluto was discovered in 1930 by astronomer Clyde Tombaugh at Lowell Observatory in Arizona. He found it by comparing photographic plates taken on different nights and noticing a tiny point of light that had moved. For 76 years, Pluto was classified as the ninth planet. Then, in 2006, the International Astronomical Union changed the definition of a planet, and Pluto was reclassified as a dwarf planet. The decision sparked enormous public debate, but the real scientific mystery was never its classification. The real question was, what was actually happening on Pluto? What was happening on its surface? What controlled its atmosphere? Was Pluto simply a frozen relic left over from the formation of the solar system, or was something much more complicated happening there? For most of Pluto's history of observation, scientists couldn't answer those questions. Even Hubble could only produce relatively blurry views of the tiny distant world. Astronomers knew Pluto's approximate size and mass, knew it had an atmosphere, and knew it had a large moon called Charon. But the details of its surface chemistry and atmosphere remained difficult to understand. Everything changed on July 14, 2015. After more than 9 years of travel, NASA's New Horizons spacecraft made its historic close approach to Pluto, passing within about 7,800 miles of the surface. What New Horizons discovered completely changed the way scientists viewed Pluto. This wasn't a dead, frozen rock. New Horizons revealed enormous mountains made largely of water ice, vast nitrogen ice plains, complex geological structures, and a thin atmosphere surrounded by layers of blue haze. Pluto was far more dynamic than anyone had expected. The famous heart-shaped region, Sputnik Planitia, became one of the most recognizable features in the outer solar system. Its surface appeared remarkably young and active, suggesting that Pluto had geological processes capable of reshaping its surface despite receiving only a tiny fraction of the sunlight Earth receives. But New Horizons had one major limitation. It was a flyby. The spacecraft had only a short window to observe Pluto before continuing onward. Its instruments were incredibly capable for their time, but they could not provide the full infrared picture scientists wanted. That's where James Webb changed the game. Webb's mid-infrared instrument, MIRI, allowed astronomers to examine Pluto in wavelengths that reveal information about temperature, surface composition, and atmospheric chemistry. Infrared light works almost like a chemical fingerprint. Different molecules absorb and emit light at specific wavelengths, allowing scientists to determine what materials are present even when they cannot see them directly. And Pluto turned out to be much more chemically complicated than earlier observations suggested. One of the most important findings involved Pluto's atmospheric haze. Scientists had previously proposed that the haze might play an important role in controlling Pluto's climate. Instead of the atmosphere being controlled mainly by gases such as nitrogen, methane, and carbon monoxide, tiny organic particles suspended high above the surface could absorb sunlight and emit energy back into space. In other words, the haze could act like a planetary thermostat. Webb observations provided powerful evidence supporting this idea. The tiny particles in Pluto's upper atmosphere absorb solar energy and then radiate heat away. This process can significantly cool the atmosphere and changes how scientists understand the energy balance of the entire Pluto system. That discovery matters because haze-dominated atmospheres may not be unique to Pluto. Similar chemistry could help scientists interpret other cold worlds, including Triton and some distant exoplanets. But Pluto's story becomes even more interesting when we look at Charon. Pluto and Charon are so closely connected that they are often described as a binary system. Charon's surface contains water ice and dark reddish material, especially around its polar regions. Scientists believe some of the organic material in the Pluto system can be transported through space and altered by radiation, eventually producing complex compounds known as tholins. These reddish materials may help explain the strange appearance of Charon's polar regions. Webb has also helped scientists investigate chemical compounds on Charon, including carbon dioxide and hydrogen peroxide. Hydrogen peroxide is particularly interesting because it can form when radiation interacts with water ice. That means Charon's surface isn't simply frozen and unchanged. Even at the enormous distance of the Pluto system, sunlight and cosmic radiation are continuously modifying surface materials and producing new chemistry. Pluto itself also contains a surprising collection of organic and icy compounds. Webb's infrared observations have provided information about methane ice, isotopic forms of methane, ethylene, and the thermal behavior of Pluto's atmospheric haze. Together, these observations paint a picture of a world that is far more chemically active than its appearance suggests. And this is where the story connects to something much bigger. Pluto's haze may provide scientists with a natural laboratory for understanding atmospheres that contain complex organic particles. Those same kinds of particles can influence how atmospheres absorb and release energy. That matters enormously when astronomers study planets around other stars. When Webb observes an exoplanet and detects atmospheric haze, scientists need reliable physical models to understand what that haze is doing. Pluto provides an actual world where researchers can study haze chemistry and atmospheric cooling directly. The implications may even reach back to Earth. Early Earth had an atmosphere very different from today's. Before oxygen became abundant, our planet contained nitrogen and carbon-rich chemistry that could have produced complex organic hazes. Understanding how haze behaves on Pluto may therefore help scientists better understand atmospheric processes that occurred on the young Earth. And that leads to one of the biggest questions in science. How did the conditions necessary for life emerge? Pluto obviously isn't Earth. It is unimaginably colder, farther from the Sun, and completely different from our planet. But nature often uses the same chemistry in completely different environments. A frozen dwarf planet at the edge of the solar system can therefore become a laboratory for understanding chemistry that may have existed billions of years ago on Earth, and chemistry that may also exist on worlds orbiting distant stars. The most remarkable thing about Pluto is how much changed once scientists finally had the right tools to study it. For most of human history, Pluto was nothing more than a faint point of light. New Horizons transformed that point of light into a real world filled with mountains, glaciers, haze, and geological activity. James Webb has taken the next step by revealing the infrared fingerprints of its atmosphere and surface chemistry. And the more closely scientists look, the less Pluto resembles the simple frozen object people once imagined. It is a dynamic world with an evolving atmosphere, complex organic chemistry, and a remarkable relationship with its largest moon. Pluto waited nearly a century for humanity to build instruments powerful enough to investigate it properly. Now we finally have them. And perhaps the biggest lesson isn't that Pluto is strange. It's that the universe repeatedly surprises us whenever we develop a better way to look.